There's a reason a lot of things in supply chain happen just in time and just in the right quantity that matters, is because it's efficient. There's a big time lag between transmission and generation and load. That puts upward pressure on rates everywhere. The dynamics of the utility space right now is just off the charts, and flexibility has never been more important. And I think co-ops are in an incredible position as kind of emperors of their system between transmission, distribution, and capacity to say, how can we co-optimize the least cost system so we keep up with this new load growth, that we continue to manage this high renewables penetration and do it in a least cost and eventually decarbonized way.
That's John Igo, the Vice President of Business Development at Mainspring Energy. And he's talking about re-envisioning the grid. The emergence of megaloads coupled with greater renewable supply necessitates the need for flexible generation. But just where are we going to find that flexibility? Hello, I'm Terry Vishwanath, your co-host of Power Plays and the energy economist here at CoBank. As always, I'm joined by my colleague, Tamara Reynolds, a managing director here at the bank. Hello, Tamara.
Hey, Terry. Let's be clear. In this rising cost environment, no one wants to pay for excess capacity that's not going to be immediately utilized. We've spent time recently considering what a no-regrets decision might look like from a system planning perspective, as co-ops stay the course on their dual mission of affordability and reliability. And our speakers today, John Igo from Mainspring and a policy and economic expert from Wärtsilä, David Millar, suggest that today's energy markets require a deeper conversation on smaller, modular, flexible, and decentralized power plants. So that's the conversation that we're going to engage in.
Our technology conversation begins with David Millar from Wärtsilä. Wärtsilä is a well-established, widely respected manufacturer of power generation technologies, specifically reciprocating internal combustion engines that have a proven track record for timely grid balancing. These engines are capable of starting and stopping quickly, adjusting power rapidly, and operating at various loads.
David begins our discussion by taking stock of the current market conditions that have prompted our collective industry discussion on power supply and the possible need for new solutions.
There's no doubt that we have resource adequacy challenges in this country, and you can see that in the NERC report. There's a few reasons why. One is that we have a lot of renewables that are coming on the system, and in fact, 95% of the projects in the interconnection queues are renewables and storage. But that actually has the impact in energy markets of depressing prices and adding more volatility. And that's a pretty challenging environment for legacy baseload generation. On top of that, we're finally seeing load growth for the first time really in a couple decades. That is a very fundamentally new world. And this, of course, is driven by data centers, electrification of different types of industry. And then the third piece is that we've seen more and more extreme sort of weather events like Winter Storm Uri, Winter Storm Elliott. We're sort of seeing through those events that a lot of our thermal fleet is actually has some reliability issues and have lots of forced outages, probably more than we thought and more than we had sort of accredited those capacities to deliver. So we see basically that there's more fragility in the system. It highlights a sort of urgent need to reinvest in our power supply. And that's what you see, I think, in PJM especially. And PJM is where Northern Virginia is, and that's really the epicenter of where the data centers are all trying to get built.
And it's certainly showing up in price, right? When you think about the capacity auction that just finished, the auction produced a price of $269 per megawatt day. And this compares to what was $28 a year ago for the 2024-2025 auction. So we are seeing prices respond to a market that is now apparently short. Are these price signals sufficient to see a power supply response, in your view?
We'll see. To date, I think the power prices in terms of the absolute prices in wholesale markets, we've had between renewables and very, very cheap gas, the consumer has benefited from pretty cheap wholesale power prices for a long time. So there really hasn't been much incentive from the capacity side or the energy side to build. And so we really haven't built much new generation in a long time. All of a sudden, as an industry, we got to get in gear very quickly and start to build I think there's some initial signs that we're going to have a response. I think if you are trying to buy a gas turbine today, it's going to take you several years to even get the parts that you need to build. So we are really running into a sort of a supply chain issue there as well. Interconnection queues across the country are still jammed up, and a lot of projects in those queues will sort of, evaporate. So it's been a really difficult challenge to try to respond quickly. And frankly, the load is being built without any sign of abating.
David makes an excellent point that a functioning market is one where if you show a high enough price for a long enough period, suppliers will respond. But there might be harder to move barriers that could prevent getting power supply to market. That backlog grew by 30% last year, with nearly 2,600 gigawatts of generation and storage capacity now actively seeking grid interconnection. This is more than double currently installed generation capacity. The last big build-out in transmission for high-voltage, long-distance wires occurred more than a decade ago. And this is a problem if the goal is to transition the grid efficiently and reliably. Here's what David had to say.
There's no doubt that we need to build a lot more transmission in this country. And a typical new transmission project is going to take more than a decade. I mean, if you're just looking at past history, it's an extremely complicated process that involves a lot of local land permitting decisions, and then generally a lot of back and forth about which states benefit and which states have to pay. It's super complex. I mean, there's a new FERC regulation, Order 1920, which is supposed to provide guidance and try to facilitate greater regional planning and delivery of transmission. Especially, we need very high voltage superhighways of lines that cross multiple states in order to deliver remote wind or large solar sources from where the resource is to where the population centers are. It's just a fundamentally different power paradigm than when you just have many fewer but very large generation sources. So there's no doubt that we could be doubling the size of the number of miles of transmission in order to enable the kind of renewables we're talking about in a decarbonized future. So there's definitely a challenge, and it's certainly one of the things that's going to slow the deployment of renewables. And in the interim, we still need to maintain resource adequacy and reliability when we have a lot of power generation stations that should be retired, right? We sort of call them zombie plants if they have to keep going and keep going and keep going just to maintain reliability. And in general, we're trying to figure out how to let those zombie power plants finally retire.
Zombie plants. This is a funny expression that David uses to talk about higher cost resources that could economically be retired. It's similar to the natural gas switching that occurred in the 2010s with coal plants, but simply can't be taken out of commission because the highway can't get built.
A confluence of factors currently are creating a gridlock in this country. Utilities and regulators are overwhelmed working to modernize and decarbonize the grid while managing queues of generators and new loads seeking interconnection. This may lead to suboptimal outcomes if grid decision makers only see limited near-term options, such as delaying new large load interconnections or delaying retirement of existing fossil fuel generators.
And large electricity consumers, such as data centers, are taking it upon themselves to find their own solutions. My colleague Jeff Johnston and I recently published analysis on some of those novel solutions, one of which is that tech companies are increasingly looking directly to connect data centers to nuclear plants. 3 Mile Island, known for being the site of the worst U.S. nuclear energy accident, is now at the forefront of efforts to expand nuclear capacity to meet rising electricity demand. But what are the other options? David expands the discussion to include modular, flexible, and distributed power supply resources.
There's a lot of challenges with trying to take off some of our legacy thermal fleet, right? And especially in the face of large growth. A lot of utilities, we look at their IRP plans and they have this default move towards, big gas combustion turbines, combined cycles, or they're just going to run their existing coal, their existing, steam generators from that were built in the, 60s, 70s, 80s. They're going to just keep riding those as much as they can, right? And we need to actually have a better, more flexible thermal fleet to support renewables and storage as well. I mean, today we have commercially, solar and wind, and not everywhere in the country has great solar and wind resources. And batteries are a great technology for supporting renewables, but commercially and economically, we're really only looking at about 4 hours of duration of storage, battery storage. We still have to cover, the winter. We still have to cover nighttime, and we're fundamentally going to need thermal generation for a long time. And so the question is, what is the kind of thermal generation assets we want to invest in to support more and more renewables? The answer to that question is we want to have highly, highly flexible generation. Wärtsilä's reciprocating engines, they're like a car engine. They can turn on and turn off on a dime, right? It can go from zero to full in less than 5 minutes, and you can turn them on and off really without any penalties. It's a perfect complement to a more volatile power system that's driven by variable renewable resources. They're also small and modular, so they're typically in 10 or 20 megawatt engines, and you build them serially. You don't have to take the whole plant down for maintenance. You can just take one engine at a time. And also, there's just an effect of when you build more distributed, more modularly, you tend to get a lot of learnings from deploying one thing many times at scale. That means that when you build your projects, they very rarely go over budget, and you can actually keep costs down. That's one reason why large nuclear plants, they benefit from economies of scale. They have inherently a huge amount of risk because they're so complicated and they take so long to construct. I mean, that's what happened with the Vogtle plant, right? It was supposed to cost $7 billion, then it was 14, then it was 30, right? Because of various factors, but one of which is it takes so long to build those things, and you don't get any power until it's totally complete.
In addition to cost, there is some concern about fuel dependency. Let's be clear, a significant amount of natural gas-fired generation was built in the early 2000s and may not be able to operate in the next decade because of emissions concerns.
Both of the technologies that we're exploring in today's discussion have fuel flexibility here, as David explains.
I will say that, from Wärtsilä's perspective, we're agnostic and we're neutral. We basically create an engine technology that will take any fuel. We recently announced that we have a 100% hydrogen capable engine that's going to be available in 2026. And we can already burn ammonia and methanol, which are sort of leading candidates to decarbonize the shipping industry. Those are easier to keep as liquid fuels. Those would be sort of green hydrogen derived synthetic fuels. And so we can already burn those today.
Reciprocating engine technology is proven and has a very long history, finding traction, in fact, dating back to the late 1800s. But today's energy needs are great. We wanted to explore other resources that can fill the gap as we search for flexible, reliable generation.
For this discussion, we turn to John Igo at Mainspring. Mainspring was founded more than a decade earlier by 3 Stanford engineers seeking a new approach to generating clean, resilient, affordable electricity. There was a terrific Bloomberg article entitled How to Sell a Power Generator No One's Heard of. And it talks about the genesis of this company. Most of the technologies powering clean energy, that is solar cells, wind turbines, batteries, and fuel cells, have been commercially available in one form or another for decades, and now they're really taking off. Not so with the linear generator, which Mainspring started deploying in 2020. But John does a terrific job with getting us up to speed.
Mainspring's commercialized a new category of power generation products called the linear generator. And the linear generator at the highest level is just a very simple way of converting a clean reaction of air and fuel directly into high efficiency, low emissions power. We leverage this kind of window between the software world and the hardware world that is power electronics to control a reaction of air and fuel on a very fast time scale and directly convert that reaction into power. And by leveraging this flexibility afforded us by power electronics in this way, we get these really interesting and important dimensions of flexibility. And that's the flexibility in terms of ramp rate and duty cycle. So we can ramp up and down just as fast as a battery can, but we can also run a peaking duty cycle like a traditional peaker. We can also run prime or base load The second dimension of flexibility is the one that I get the most excited to go to work for every day is our fuel flexibility. We can switch fuels on the fly, leveraging these power electronics for both fuel redundancy, being able to switch over to a backup fuel in the case the primary fuel gets interrupted or is unavailable. Another dimension of flexibility is scale. We can scale to effectively any project size. These are containerized and modular linear generators. And then you can also, with this modularity, customize the level of availability and redundancy the system needs. And then the last two are around siting and location. So we have incredibly low emissions, categorically different than traditional thermal generation. And because of these very low emissions, you can permit our generators closer to load. Lastly, because they're containerized, kind of getting to the siting and location perspective, we can move these things. So if you picked a place to put these, maybe you put them next to a data center and that data center goes away someday, you can move these containers across your system and make sure that they're in the right place as you move forward to ensure they're not stranded. And if it's okay, Terry, I got to use a term you used on one of your previous podcasts. These dimensions of flexibility, we think affords co-ops and their members the luxury of that no regrets, right size capacity investment.
I want to unpack a couple of the comments you made. So for folks that are trying to get their head around this technology, so compared to a peaking gas unit, how does it compare?
So take a traditional gas peaker. Let's just pretend like it's a 150 megawatt frame machine as a starting point, and then slice it into 600 pieces of modularity that can be used to ensure that the power plant is always on, even if a small portion of that power plant is offline. That's one thing that we can do that a peaker cannot do. If we need to bring one of our modular units down for maintenance, the rest of the plant stays up. You're never losing 150 megawatts at one time. That just will not fundamentally happen. Then take the efficiency of that plant and increase it to 45% efficiency. That's on an LHV basis, so an 8,400 BTU per kilowatt hour, higher heating value, heat rate, very high efficiency product. And then know that no matter what load point you set at that 150 megawatt project, you're getting that level of efficiency because you're just turning off modular nodes at a time to run that plant. Now make it as fast ramping as a battery. There's no start time. There's no thermal inertia to spin up. These units can turn on instantaneously like a battery. They can participate in all the fast ramp ancillary services markets across the country. We have the flexibility to do that. And now make it truly hydrogen ready. Now make it truly ammonia ready. Now say put whatever fuel you want to put in there, go ahead and put the fuel in there and run the project. And then maybe one more thing. Hey, we need 20 megawatts of this project to go bring up a load over a new data center over here. Let's just take part of this plant and move it to where it's needed on our system.
Let's talk about the current marketplace and where you see application for this technology.
For the purposes of this portion, Terry, I'm just going to start small and from smaller use cases and go to the larger ones. We started behind the meter at grocery stores and other kind of C&I, commercial and industrial loads. This helped them not only reduce their retail energy costs, but also manage their retail energy cost risk because they have more certainty and they have the ability to ride through a grid outage. Then we have a great use case for Mainspring, and I wish there was infinitely abundant biogas on planet Earth for us to run off because biogas is a great use case for us, but we run prime and base load off of biogas coming from landfills, wastewater treatment plants, and dairies. Then we have microgrids. We've got microgrids at logistics hubs. We're firming rooftop solar at large logistics operations. We are powering fully islanded EV microgrids for the likes of Prologis. They've talked a lot about a project we're both very proud of, which was their ability to bring on and electrify their drayage fleet years before it would have been possible with the electric utility. And that's not the electric utility's fault necessarily. It's in Southern California where it's really hard to build out that infrastructure. And then the larger scale version of that kind of islanded microgrid is bridging power for data centers. And we're in the middle of the data center customers partnering on what the design looks like for a 3 or 5 9 installation in a place where they can't get power for sometimes 10 years. The utility muni co-op side, we've got a non-wires alternative going on with AEP in Oklahoma. kind of more traditional grid scale opportunities that look like kind of large battery energy storage projects at kind of transmission voltage. A large one that we have currently being developed is a 50 megawatt project we're building on behalf of Piesco in Colorado, where we were chosen as part of the least cost portfolio for their last large round of procurement. So something else we're really proud of is that we beat out a traditional peaker at the same location because of our ability to provide that least cost portfolio given the constraints in Colorado. One of the use cases most applicable to this audience is scalable, strategically sited capacity, particularly at distribution voltage, and this being for co-ops and munis as well, but especially for co-ops. Why distribution voltage? There's a couple reasons. One is capacity can be brought online faster because 12.5 and 34.5 kV transformers aren't as long lead as 69 kV and higher. If you need capacity before 3 or 4 years from now, you're not waiting that long. The long lead equipment's about a year, and so you can build a project and bring that capacity online. But we have a lot of customers that are looking at their battery installations, as part of their least cost portfolios and saying, we need those batteries, but they aren't capacity. They cannot run through the multi-day heat wave. Just want to make sure it's clear that even though we can flex and ramp fast like a battery, we can provide the long duration capacity to run through that scarcity event. You can keep the lights on during the next crazy thing that happens.
As John highlights, there's a reason a lot of things in supply chain happen just in time and just in the right quantity that matters. That's because it's efficient. If there's a big time lag between transmission and generation and load, that puts upward pressure on rates everywhere. That's what's happening in PJM. That's what's going to happen in other markets because what we need is for capacity to keep up with the load.
Flexibility has never been more important, and these new options might prove to be an important piece of the puzzle.
I hope all of you have enjoyed today's technology conversation and will join us as we wrap up the year next month, speaking to the energy journalists covering this year's major stories and the ideas they share about what the next year might hold.
Thank you for listening, and goodbye for now. CoBank's Power Plays podcast is intended for informational purposes only, and the information should not be used without CoBank's express written permission. The information provided in the podcast is not intended to be investment, tax, or legal advice, and should not be relied upon by listeners for such purposes. The information contained has been compiled from what CoBank regards as reliable resources. However, CoBank does not make any representation or warranty regarding the content and disclaims any responsibility for the information, materials, third-party opinion, and data included in the podcast. In no event will CoBank be liable for any decision made or actions taken by anyone, person or persons, relying on information contained in this podcast.